internal phosphorus loading in urban stormwater ponds. Vinny is also a part-time stormwater extension associate at North Carolina State University, where he focuses on urban green stormwater infrastructure projects and finding ways to partner with communities to achieve equitable results. In his free time, Vinny is president of the Twin Cities chapter of the Japanese American Citizens League, a civil rights organization committed to fighting for social justice for those victimized by injustice and bigotry. Please welcome Vinny.
Thank you, Eric. It's good to be here back at the in-person NALMS after so many virtual NALMSs, which are surprisingly great, but there's no substitute for seeing you all. So, as Eric mentioned, my name is Vinny Taguchi. I'm going to be talking about stormwater ponds, surprise, but I'm going to be sharing research that has been done by this larger research group that Ben alluded to, and we're just trying to understand how do we use these things to properly manage phosphorus. Okay. So Ben did a great job of introducing stormwater ponds, but I want to take it just a small step back, and I realized that at a lake management conference, maybe we don't all have the same background and familiarity with stormwater management structures, or perhaps we have different perspectives that we bring into that field. So these stormwater ponds are all over the place in Minnesota and many parts of the world. And the basic idea is that there's a lot of fun stuff in an urban watershed that we would rather not make it into our lakes and other water bodies that we might be managing. So they're constructed as this kind of, I should paraphrase, they're not all constructed. Some of them are natural ponds and wetlands that have been converted into a receptacle for urban stormwater. Some of them have been constructed for that sole purpose. But basically they're designed to be sacrificial to some extent and capture all of these nutrients and pollutants in order to keep the lakes clean. Now, they come in all different shapes, sizes, and colors, and how you manage them kind of depends on your priorities. Sometimes you have a pond that's treated as an amenity, it's in a very public place. We have to make sure that the water quality there also is kept to a certain threshold of quality. In other places, it's out of sight, out of mind, and you just let it go as long as downstream is protected. But when we take a closer look at some of these ponds, and the green ones in particular, we see that there is quite a bit of phosphorus and nitrogen going on in that water. And if you know about how there's meant to be protecting against phosphorus in particular, we want phosphorus to settle to the bottom and stay put. So if there's a lot of phosphorus in the water column that's feeding the duckweed like Ben was talking about, that's when we start to get worried. We want to take a look and make sure, okay, does that just stay in the water in the pond, or does it get into the water and then flush downstream? Unfortunately, green infrastructure, stormwater ponds, it's all connected to this big, larger urban watershed. Sometimes stormwater ponds drain 100 times their surface area. It's a very different loading ratio than what you worry about with most lakes. So there's a lot of dynamics that you need to take into consideration, like John was talking about with all of the organic matter and leaves that might be contributing to your ponds. But this is what we want to avoid. In particular, we want to avoid harmful algal blooms, which can happen in ponds as well. There have been a number of news stories about dogs dying as they get into the water. In Minnesota, I feel like the duckweed might actually have a silver lining of preventing some of these harmful algal blooms, but certainly that's not the solution either that we want to be having. This part I'll skip over pretty quickly, but why does this happen? If you want to go into detail, this is the paper we put out where we did some lab studies and tried to quantify the sediment phosphorus release rates in these ponds and the prevalence thereof. Basically, we linked it to mobile phosphorus, which is a combination of iron-bound phosphorus that's sensitive to how much oxygen is in there, and the metabolized organic matter from all this muck that accumulates in the ponds. So the real question is, what can we do? We have thousands of ponds, as the first two presenters mentioned, that were put in 40, 50 years ago sometimes, and it would be really expensive to replace them with anything, whether or not we get rid of them or we install some other way to protect our lakes. It would be really great if we could just continue using these ponds that we already have in an effective way. So that's what we're trying to understand. Is that possible, and how might it be possible? So there's a number of remediation strategies. This isn't even a comprehensive list, but there's a number of lake management techniques basically that you can apply to stormwater ponds as well. And there isn't a good amount of data specifically looking at stormwater ponds to know, are these still effective in ponds, And more importantly, are they cost effective? Perhaps something that works in a large lake or reservoir is not going to be cost effective for a 1 acre pond that's in a remote area. So what I'm going to focus on today in this talk is these 4 of the remediation strategies that we modeled, but I have a report where we looked at all of them. If you're interested, I'd be happy to send you a copy. So the way we went about this, we used the tried and tested water quality and hydraulic model CE_W2. This was developed by the US Army Corps of Engineers quite a bit ago, which is why it's written in Fortran and is very user-friendly. But it has been used in a lot of different applications. It's used to model lakes, estuaries, rivers, reservoirs, but to my knowledge, it hasn't really been used on stormwater ponds or something of quite that scale before. So we're definitely pushing the limit on what's possible, but it's a 2D computational model. So the way we went about this study is acknowledging that this is not going to be a 100% accurate representation of the ponds that we model. So instead of attempting to do what we feel might be impossible, we decided to say, okay, how can we make this a useful modeling exercise, where even if we're not representing real life, we're testing things in a way that we can get some useful information out of it. So what we did, we picked 4 stormwater ponds. We tried to get a variety of ages, sizes, shapes, water quality. We collected a lot of data on them: bathymetry, water quality, the wind sheltering. You can see from these bathymetry maps, those are in centimeters. So we're looking at ranges of less than a meter to about 3 meters. These are very shallow systems. That certainly had some consequences for how we go about modeling it. When you're looking at a large reservoir, you may have a vertical resolution of 10 meters, maybe 1 meter on the really fine side. We were looking at 15 centimeter partitions. This is some more information about those ponds if you're interested. I can always come back to this if you have questions. But the other thing we had to figure out was, how do we model the presence of duckweed? This effort started about maybe 2 years ago, so we still didn't know quite as much as what Ben just presented. We knew the duckweed is there, it's really thick, and it has to be doing something. One thing we knew was going on is it's definitely going to be affecting how deep the light penetrates into the water column. So we collected measurements from our ponds, these profiles of temperature that Ben mentioned. We've also been recording observations of what % of the pond surface area is covered in duckweed and wolfia and all these floating macrophytes. And we expressed that in the model. This was some calibration that went on to find these values. But basically, we wanted a light extinction coefficient for when the duckweed is not there, interpolated up to a value that was representative of when the duckweed was there. So that when we calibrated our model, we have the heat from the sun being dissipated appropriately throughout the water column. The other thing we ran into was, since we had such fine vertical resolution of 15 centimeter increments, we started running into the issue of numerical diffusion. So just by having 2 cells next to each other and trying to balance out the concentrations, we were having a hard time calculating the chloride that is present in these ponds and the stratification that comes out of it. Everything was dissipating very quickly in our model. So what we had to do was really crank down the diffusion and dispersion mechanics within the model in order to get something closer to our measured levels of chloride and the stratification from it. We were not able to get anywhere near what we observed, but we were able to get enough to where our model could say there is stratification from chloride or there is not stratification from chloride at a certain point, which was helpful. And then here is just an example of the model output. So here we have the temperature stratification over this modeled field season. You can see the chloride stratification and the cumulative density, which is what's really resisting the mixing. Then we look into phosphorus, because that's ultimately what we're trying to figure out here. Is there phosphorus being released from the sediments? And you can see we were running into issues with the particulate settling. So this computational model, since it's used for reservoirs and lakes and things of that nature, a large portion of the phosphorus is going to be in a particulate form tied to sediments and erosion. And so that settles very quickly, and that's an important feature for them to capture. But in our ponds, we have such a high fraction of the phosphorus in the organic matter, these fine particulates that really don't settle within the residence time that the water is in these ponds. So we basically had to turn off particulate settling in this model in order to get get the phosphorus to linger in the water column about as long as we were seeing in the field. Part of that could be what John was talking about, where the data that we're informing this model with, where we sample how much phosphorus is coming in, does not include all of the bulk organics and leaves. We just don't have the methods in place that John is currently developing. So because of that, we had dissolved phosphorus concentrations, and we needed to make the pond represent the phosphorus that is actually in the pond. So we needed to make some allowances for that. So now getting into the treatment methods that we looked at. So of course, watershed-based practices, these are, I guess, preventative rather than reactive after the fact. Anything preventative is usually going to be cheaper than dealing with the problem after it. So if you have a pond that does not have this internal phosphorus loading problem, we thought these would be attractive options. So of course, managing the leaf litter and pollutants coming into the pond, or perhaps managing the stormwater altogether by reducing the volume, infiltrating it, capturing it. Another way to do this would be installing some kind of structure upstream of a pond. There's usually a manhole. So if you install a baffle, you can capture a lot of the leaves, sediments, and trash. What we did for the model, since we're just feeding into it how much, what phosphorus load is coming into the pond, we experimented with some different reductions in either the total volume of stormwater, so we kept the same concentrations that we have coming in over the season, but reduced that total volume, and then calculated based on literature, how many rain gardens would you need to apply in your watershed to get that level of reduction, and what would that cost? The other way we went about it was a percentage concentration reduction. So that'd be if you do a lot of street sweeping but otherwise don't manage the stormwater, so you have the same amount of water coming in but it's at a lower concentration of phosphorus. Again, similar calculations based on research. And this is what it looked like for the phosphorus results. So here on the left, I've got the impact on phosphorus export. This is what comes out of the pond. So if you're managing a lake downstream, this is what you care about. On the right, we're looking at concentrations in the pond. So if you're managing the pond itself for water quality, this is what you care about. And we evaluated each of the remediation strategies in this way. So here on the left, each of our 4 model ponds, you see that as from the original condition in blue, as we reduce the volume, you see a sharp drop. So there's obviously much less phosphorus coming into the pond, but there's also much less phosphorus coming out because there's less water coming out of the pond. So the pond itself may still be accumulating phosphorus, but it's not getting downstream. When we look at concentration reduction, so just street sweeping, obviously you still have a lot of water leaving the pond, so then the concentration of the phosphorus in the pond itself and the sediment phosphorus release still come into play, but you still get somewhat of a reduction. But when you're looking at the pond itself for water quality, if you're just reducing the volume of the water but not the particulate matter, you actually see an increase in phosphorus concentrations in the pond because it's going to be concentrating, and that makes sense. But if you reduce just the concentration, then you can see an improvement in the water quality of the pond. So again, kind of depends on what your management goals are. So next we look at chemical treatment of sediments. So I don't need to talk to the NALMS audience about alum and these other products that are out there. These pictures were provided by Joe Bischoff. So it says Stantec there because he was formerly with Wank, and then that got turned into Stantec when he sent me the pictures. Now he's at Bar. But basically taking this lake application method of barge releasing chemical treatments, and Joe and his team and some others in Minnesota have been experimenting with a smaller scale version where you take a raft and do these treatments in something small like a pond. The other thing that we're experimenting with in Minnesota is iron filings treatment. So you can go around with a tractor in the winter because you can drive on your ponds in the winter here and release iron filings or any kind of particulate chemical treatment in a way that we're hoping might be more cost effective than using a barge in the open water season. So the way we model these, again, we don't have like the mechanisms in the model to actually see is this treatment effective. We had to rely on literature values to say this is the expected rate for this expected dose, and then what would be the cost of that dose. So we put that into the model and see if we reduce the sediment phosphorus release rate, obviously we see some improvements. We don't see improvements for these ponds, this is for TP export, for the because they just don't export that much phosphorus to begin with. There's not much water leaving them. So if you completely reduce it, it's not really changing. But then for total phosphorus concentration in the ponds, you see improvements as you apply some kind of chemical treatment. except for the Langton Pond. So the Langton Pond is one of our newer stormwater ponds. It hasn't accumulated that much organic matter, so it doesn't have that much sediment release yet. So there's nothing to treat with this method. This would be a pond where you might want to do more of a preventative approach. Then we've got mechanical aeration. As Ben was mentioning, you have to make sure you do this well. So you don't want to just install something that's going to suspend all of the sediments in muck, or else you're going to be dealing with more of an issue than you had to begin with. We also, feel free to send me some information if you have seen this in your experience, but we haven't seen where fountains are really an appropriate solution for this. Typically they're just spinning around the water that's at the surface or a very narrow footprint. And what we really need in order to overcome the stratification across a pond is a distributed network. So really you would have multiple of these bubble plumes that are mechanically mixing the pond. So it's not about injecting oxygen into the water. Those methods exist, but it's probably going to be too expensive for a pond. But this is just releasing air bubbles that mechanically turn over the water in a way that the wind should be doing, but as Ben demonstrated, isn't. So in order to make these calculations, we relied on a lot of information from practitioners. Algae Control Canada in particular provided us estimates based on their work of what density of bubblers you actually need in these shallow ponds. So in a large reservoir that's deeper than it is wide, you can probably get away with 1 or 2 of these bubblers. But in a very flat and shallow stormwater pond, you need a lot of these points distributing it in order to mix it all, and they provided some costs associated with that. So as we see with the mechanical aeration, we also get improvements, but again, we weren't able to test this mechanistically in this model. That's just a limitation of the model. So we had to measure the oxic condition sediment release rates of phosphorus in our ponds and then apply that into the model. So you see improvements in all of them except the Langton Pond, which doesn't release much to begin with. Then wind sheltering reduction that Ben mentioned. I'm running out of time, so I'll go quickly, but basically the theory that we don't want to cut down all of the trees around a pond, but a lot of times when they're built, you don't have trees to begin with, so perhaps you can just manage them proactively from the beginning and not run into the issue of sheltering. But if you do have a pond that's sheltered, maybe there's also a proactive management technique that you can use where you just figure out where are some strategic places that you could remove trees to allow the wind to come in, and perhaps you can replace them with something that's still seen as an amenity, like prairie ecosystem, pollinator habitat. Just because we're losing trees doesn't mean we're losing ecosystem services. So the way we went about testing this one, and this one, most of the credit goes to Dr. Bill Herb at the St. Anthony Falls lab, but he developed a 3D computational fluid dynamics model using a software called ANSYS Fluent, and tried to calculate how much sheltering is truly attributed to these trees and buildings and topography around the ponds, and how would that change as you remove the trees. So we basically calculated in each orientation that the wind could be blowing, how much sheltering are you getting, and what you can reduce that to, what would it cost to remove all these trees. Unfortunately, we can't calculate the cost of all the phone calls you're going to get if you're just clear cut. So again, our study, we're looking more at these strategic opportunities that are going to be cheaper and meet less resistance. But when it came into the model and we applied this new wind inputs from the model after having removed trees, we were surprised to see that we didn't really get that much of an improvement. And perhaps there's something with the model I don't quite understand, but from what we could figure out, it seems like it's just not as sensitive to it as we would have thought. So it's hard to say whether that's an artifact of the model or it's something that's truly going on in these ponds. Something I've noticed anecdotally just being out in the field is that, so this is a pond that's got quite a large forebay and then the main body of the pond. So here it's exposed to the same wind at the same time, similar sheltering around it. And you can see that the water in the forebay is completely quiescent and the water in the main body is very choppy. So I think just the size of these ponds, or perhaps the topography of these banks on the sides, may be enough to provide sheltering so the trees are not the full picture. And Ben did some additional Bill did some additional modeling to try to show the effect of that topography. So running out of time, so anyway, we compared all of those based on effectiveness as well as cost to try to recommend for different kinds of ponds what would be the better alternative. There's not one solution that works for everything. You definitely have to know something about your sites, but happy to take any questions if there's time. Thank you.
think in the interest of time, just to keep on time, we'll move on to our next